Good morning. Hello. Thank you so much for joining us today. I'm Laura Betts. I'm our communications team lead for NASA's James Webb Space Telescope from Goddard Space Flight Center. We're here at Northrop Grumman Space Park today for a very special event. We are going to be showing you some footage of Webb's telescope's mirrors opening one last time here on Earth. The NASA's James Webb Space Telescope is the largest, most powerful, and most complex space telescope ever built. A revolutionary successor to NASA's Hubble Space Telescope, it will examine every phase of our cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets, to the evolution of our own solar system. Peering back 13.5 billion years into the past, when the first stars and galaxies were forming, Webb will capture images and spectra that will fundamentally change our understanding of the universe. Today, you will hear from NASA experts working on this groundbreaking mission. You'll see never before seen footage of a test that unveils the mirrors as they will look for the last time on Earth. And you'll have an opportunity to ask questions about this mission to our experts. So let's get started. This event is being streamed online, and reporters are able to ask their questions by raising their hand or raising their hand on Zoom. For the public audience online, you can use hashtag NASAWeb or hashtag AskNASA for your questions. I'm excited to hear what we'll learn, and this Zoom session is being recorded. First, let's take a look at how these mirrors have moved across the country where they were assembled, built, and tested for this telescope. Thank you. So that's an incredible progress with those mirrors traveling all around the country where they're built onto that assembly frame at Goddard Space Flight Center, traveled down to Johnson Space Center in Houston, and are now here at Northrop Grumman Space Park. So we're going to be hearing from Webb's Program Director, Greg Robinson. Greg?
Thank you, Laura. So good morning and welcome. We really appreciate you being here in person, to the ones who braved it, and certainly virtually as well. We really appreciate you guys continuing to keep the interest high in our science and exploration programs, and certainly for James Webb, like no other. Often say that's on the science side, that's our Apollo, our shuttle, our International Space Station, and our Hubble. We really look at it on that scale. So thank you for continuing that interest and that communications. So I'm gonna talk a little bit about the where we are today, and Bill and Scott are really gonna give you the details of that. So we're getting pretty close to shipping and launch. Over the past year in this pandemic environment, families and employees have learned to live and work together like we would have never imagined, and we still kept this observatory going through INT. So I definitely take my hat off to the team, the resilience, whether it was travel on site, dealing with testing, vaccinations, and everything else. We still kept the thing moving. So we're just a few months from shipping, which will be in late August per plan. When we ship, the schedule margin will be pretty close to zero, but still on plan. and we have a couple of months of processing at the launch site, as you hear more from Bill and Scott on that. So really, really good progress over the past year, and again, especially in the COVID environment. Another thing you will hear a lot today, hopefully, you will hear a lot of, we tested this for the last time. We deployed that for the last time. We just did the final stow. We did the last deployment we will ever do on Earth. You will hear a lot of last times, finals, and so on. So all of that means for Sports Scout, we're getting pretty close to the goal line, and we just need to punch it over. Right now, we're not working any liens against completing all of the planned work, which is really good. And you'll hear more about that as well. So right now we're in a really good place. Of course, we have all the reviews coming up. You hear more about those as well to get us to ship and launch. And when we get to the launch site, we'll start the launch processing right away and plan to connect with the Ariane 5 rocket to put us in our appropriate orbit. Lastly, I will say, in addition to the observatory, which is pretty important, the most important is really the science. So you're going to hear from Begoña, you're going to hear from Klaus and from Eric about the amazing science that Webb will provide. And we often say it's going to rewrite the physics books. We're looking forward to that. It's going to unlock many of the secrets and mysteries of our universe and even our solar system. So I'm looking forward to hearing that as well. And with that, thank you, Laura.
Thank you, Greg. We're going to be hearing now from Bill Ochs, our project manager for NASA's James Webb Space Telescope, and Scott Willoughby, the vice president and program manager space systems at James Webb Space Telescope at Northrop Grumman. So let's hear from Bill. He's standing live in front of the telescope.
Thank you, Laura. As she mentioned, my name is Bill Ochs. I am the project manager for NASA for the James Webb Space Telescope. And you can see behind me, Scott and I are in the viewing area of that clean room of that incredible engineering and scientific machine known as JWST. What I'd like to do is give kind of a program overview of where we've been over the last couple of months and what we have left in front of us. Over the last few months, we have pretty much completed almost all of our deployments that have been associated with all of our post-environmental testing. That includes things like the solar array, radiators, one of the telescope wings, which we'll talk about later, as well as the very complex and challenging final successful deployment of the sun shield, which now has been folded back up and it's in the process of its final stowing. In addition, we completed the final electrical test of the entire observatory, as well as the final ground segment test where we actually command the observatory behind us from the Mission Operations Center that is in Baltimore, Maryland, on the campus of Johns Hopkins at the Space Telescope Science Institute. So now let's talk a little bit about what's left in front of us. So either today or tomorrow, we will be deploying the final wing. We do some closeout work behind that. We then stow that. We have to complete the stowing of the sun shield and the activities that are going on there. Scott will talk some more about that later. In addition, one of the more critical activities we have is before we started the observatory electrical test, we did have some issues with a transponder, or two transponder boxes. A transponder is what we use to communicate to the spacecraft. Those transponders were taken off the spacecraft. They were sent back to the vendor. It was a workmanship issue that had degraded over time. They finished all that rework. They're in the process of doing unit level testing now. Those boxes will come back in mid-June, and then we will execute a battery of electrical tests as well as testing with some of our critical ground elements like the Deep Space Network and the Space Network to ensure that everything works properly. When that is completed, all really that's left is completing up the preps that we need to put JWST into its shipping container. So let me now switch over to operations and ground system. As I mentioned, the operations of JWST is done at the Space Telescope Science Institute located on the campus of Johns Hopkins in Baltimore, Maryland. The ground system is done. We're in the process now of finishing up some final verifications of some of our operational products. And at the end of April, we actually entered a ground system freeze that occurs prior to launch. What that means is that the only time we will make any kind of change to the ground system is if it's something that we need to do for mission success in the first few months of the early life of on orbit with JWST. In addition, we are continually executing rehearsals. We, either with a small team or with a large team, we walk through the launch countdown, launch and ascent. We go through various portions of the timeline, of the commissioning timeline, to make sure we keep practicing and practicing. And a good example of that is next week, we will be doing a rehearsal that lasts from Monday through Saturday. And we're going to go through the sunshield deployment. The simulation team will actually throw anomalies at us, and it'll be a way to test our ability to respond to anomalies and correct the problems of what we may see on orbit. We are also preparing for the launch site activities. We leave for the launch site in August. We will be down there about 72 days. The observatory is down there about 55 days. Over the last couple of months, we've done things like practice and train fueling of the observatory down at the launch site. That was done at the Astrotech facilities down at Kennedy Space Center. We've delivered the shipping container out to Northrop. It's in its final preps. And we're wrapping up the development of the procedures that are required for the approximately 1,000 tasks that we need to do down at the launch site. And they'll be all wrapped up this month. And then finally, Begoña is going to give some more of the details of the commissioning timeline. That timeline is now very stable. It lasts 6 months. We've developed over 300 plans and procedures for contingency operations, can give us a toolbox on orbit. And as I mentioned earlier, we practice, practice, and practice. So that's kind of my presentation. I'm going to turn it over to Scott. He's going to give you more of the engineering details. Before I turn that over, I did want to thank publicly the thousands of people who over the years have worked on JWST. We would not be where we are today without the dedication of those folks, or where we're going to be a year from now doing the amazing science that we'll be doing with JWST. And with that, I'll turn it over to Scott.
Well, you've got an exciting moment here that really wasn't planned, because we tried to plan this briefing for when we'd have one of the wings deployed. You'll see a never before seen footage of actually deploying of the wing on this side of the telescope. But what you're watching right now is us getting ready to deploy the wing on the other side for the last time, as Greg mentioned, on Earth. We're going to prove that that works, and we have to do it by simulating a zero-G environment, meaning we have to effectively have that mirror float like it does in space, because we design these to operate in space, but we have to test them on the ground. And gravity could be pretty humbling in how complicated it is to open things that are out there. And you're watching somebody on a scissors lift now, and on a diving board that's coming across. These are the brave and talented souls that work on Webb that are in this high bay 20 hours a day, 6 days a week, a seamless team between NASA and Northrop at this stage in the game, readying to hook up this offloading equipment such that tomorrow we'll open another wing, get another video out of that. And that is one of the last major deployments. And then right now you're seeing the mirror with its ears pinned back. We've designed and built an optic bigger than the top of the rocket. So the rocket's 5 meters in diameter on the top, the mirror is 6.5 meters in diameter. So with that, you had to create a deployable mirror. You stow it for launch and deploy on orbit. So absolutely incredible. And I mean, what an exciting moment. Actually see the folks in work here. I think it's, you know, it's more exciting than even seeing that with a mirror open, because you're going to see plenty of pictures. So Kevin, if we could just show the short video now so you can see what we had just done a little over a week ago, maybe 2 weeks ago here, in deploying one of the wings, and what we can get ready to do on the other side tomorrow. So welcome back. I kind of get chills watching that. I'd like to say I'd want to have that job, but Bill and I had one chance to go 10 feet high on a scissors lift in the high bay, and then they brought it back down and they sent us to our offices. So we're not going to be 40 feet standing in the ground at the end of that. And this, It's an incredibly dedicated team that's out there, and as Bill thanked the thousands of folks I do, we have the privilege of being the last stop in the U.S. on this journey here. A billion miles away into space. For your chance to see this and witness this, and then of course follow along the rest of this journey. It's absolutely thrilling to represent this team that you can see out there, doing this incredibly precise work on the grand scale. It's like building a Swiss watch that's 40 feet tall and 80 feet long and 40 feet wide, right? And getting it ready for, this journey that we take it into vacuum and minus 400 degrees Fahrenheit, 4 times further than the moon, right, to deploy this mirror. So anyway, thrilling moment to watch behind me. And then I try not to look too much usually when I get in this moment. I go back to my desk and let the technicians do their job. But that's what I wanted to share. So I'll hand it back to you, Laura, and I think Begoña.
Before we go on, Scott, could you just tell me about how they pick people to work on those diving lifts, or how do you go about that? Because it's just a really fascinating aspect of the job here.
One story that I think is true, maybe part myth, is when you're going to be a technician working in this high bay and you come in, they put you in a basket and they ride you all the way to the top of the ceiling and see how well you do in a very safe space. But what really happens is everything that gets done here on Webb, it's an amazing, feat, but we have a full-scale sun shield in another building. At NASA, they had pretty much a full-scale center section of the optics in their high bay back at Goddard, in Maryland. And before you come and work on flight, you have to go through the practice field. You work your way to AAA, and you hope you get selected to be on the team, to use Greg's sports analogy. So it's a lot of practice and exposure, because the first time you go up there and you look down, that can't be the first time, right, when you're doing it on flight hardware. So the team goes through a tremendous amount of practice. And at this point in time, the people that are up there are only the people who've done it before. Bill and I have a rule is there's times where we've, delayed a test basically to assure that the technician, the test conductor, the engineering are a part of that operation, such that last time the familiarity with that, tough word to say, right, is with those folks, along with the muscle memory and the training. So they go through a lot of hoops to make it to the pros.
Thanks. Yeah, it's fascinating. It must give them goosebumps to be working on it. All right, let's head back into the auditorium and hear more from Begoña Vila, our Webb Instrument Systems Engineer from NASA's Goddard Space Flight Center. Begoña?
Hey, thank you, Laura. So I want to tell you now a little bit about the parallel activities that have been happening with all the items that have to be done with the flight hardware that you have been hearing. We also have to prepare for what we are going to do once James Webb is on orbit, to commission that observatory. And this is a work of years that has been happening in parallel with the hardware testing on the other side. So we have a timeline that starts a few days after launch and lasts for 6 months. And we know exactly what we are doing hour by hour, day by day during that time. The commissioning can be divided top level into 3 main phases. The first one that lasts approximately 30 days after launch is related to all the deployments that you have been hearing about, where we open the observatory from its folded state inside the rocket to its full glorious size. And it also includes some of the maneuvers that need to happen to get the observatory exactly where it needs to be, those 1 million miles away. After that, the next phase that we have to do is align those mirrors that you are seeing. When we take the first picture of a star on orbit about 40 days after launch, instead of a single star, we are going to see 18 stars, because each of the mirrors behaves as a single mirror. So the work we need to do is identify which star belongs to which mirror, and then bring them all together. So at the end, we have a single star that looks very nice, that is very well focused for all the instruments to use. This process is called wavefront sensing and control, and we had the chance to test it with the flight hardware at the cryo testing in the Johnson Space Flight Center. After the mirrors are aligned, the instruments have already been powered in parallel because they were used to take images to help align the mirrors. But they are waiting for that final state of the alignment to start their own commissioning, the detailed commissioning for their observing modes. That happens at around day 120 and takes about 2 months. And during that time, all the instruments will check their mechanisms, will check their detectors, and will generate these reference data files that are needed for normal operations. When we launch, we have a version of those files and that we were able to gather on the cryo testing of the instruments, which was done at the Goddard Space Flight Center. But that needs to be updated with the on-orbit information. In parallel with all of this, if you can imagine, when that sun shield opened a few days after launch, the cool down of the observatory started. The instruments and the mirrors started their cool down to get to those amazing close to 0 temperatures. And that cool down needs to be monitored. There are activities that we need to do, and we do that as well in parallel throughout that time. Now, to help us generate and validate this detailed timeline, we have very high fidelity simulators that are at the Mission Operations Center in Baltimore. So then those simulators duplicate the whole observatory and let us send commands and receive responses as if we were working with a real flyhouse that we cannot do. And then, as Bill mentioned, we have a very detailed set as we are getting close to launch of launch rehearsal exercises where the team, the same team that's going to be there during commissioning, is in the control room and will run through activities of that timeline, normal mode and also contingencies to make sure we are ready for operations. So at the end of this 6 months period, each of the instruments will have declared their various observing modes ready for science. And I think you are going to hear all the wonderful things about that science now from Eric and Klaus. Thank you, Laura.
Thank you, Dr. Vila. So now we're going to head to Eric, who is our program scientist from NASA headquarters, and Klaus Pontoppidan, who is the project scientist for the James Webb Space Telescope, for a little more information about why exactly we're launching this space telescope in general and what sort of science we're going to get back.
Thanks, Laura, and thanks, Begoña, for that description of how we'll be getting Webb ready for science. Why have we built this fantastic general purpose observatory in the first place? It's true that Webb can address most broad areas of astronomy, but it was born out of a specific need. To understand that need, we'll travel back in time to the mid-1990s. In 1995, the Hubble Space Telescope performed what proved to be one of its most important observations. It stared at a blank patch of sky for 10 days. The image that came out of that observation was not an empty black void has been previously seen, but rather it was a beautiful jewel box, if you will, filled with undiscovered galaxies, thousands of them, of all shapes and colors strewn across the field of view. As astronomers studied these galaxies, they looked for signs to see if any of these were part of the first galaxies to form after the Big Bang. None of them were. So NASA's most capable telescope could not see back to the time when the universe began to form its first stars and galaxies. Now, in the early 2000s, NASA's infrared observatory, the Spitzer Space Telescope, similarly looked for early galaxies, and it too could not find them. So both of these observatories, incredibly successful in their own rights, were not capable of capturing this very faint light from the universe turning its lights on, as it were, after the Big Bang, because they either didn't have a large enough mirror or their wavelength coverage was not optimized to detect these faint objects. So out of this realization, the idea for Webb was born. So from the start, Webb was envisioned as the observatory that would help resolve one of 20th century astronomy's biggest quests, which are namely, what are galaxies, these collections of tens to hundreds of billions of stars, how and when did they form and evolve over the more than 13.5 billion years of cosmic time. Now, since work began on Webb, we've come to know that our local neighborhood contains thousands of exoplanets, planets orbiting around other stars. And so even though Webb was not initially conceived as an exoplanet mission, it has instrumentation that will propel this new and exciting field into its next epoch of discovery. Webb's giant mirror and infrared coverage will let scientists probe atmospheres of exoplanets to look for water, carbon dioxide, methane, and other compounds that could indicate habitability. In other words, exploring the atmospheres of worlds that could host life. Now, in between these two extremes, the most distant galaxies whose light was emitted when the universe was young to nearby planets around other stars, or even in our own solar system, Webb is going to study all phases of cosmic history and many different types of phenomena. Webb's infrared capability means it can see into dust clouds that conceal forming stars and planets and learn how those stars are born. And Webb's innovative multi-object spectrograph will pick out thousands of individual galaxies from many epochs in the universe's history to see how they change over time. Now, these are the type of investigations that we planned for or came to realize were possible with Webb as we were building the observatory. Of course, the discovery capability of Webb is limited only by our own imaginations, and scientists around the world will soon be using this general purpose observatory to take us places we haven't dreamed of going before. And to tell you about what Webb will be doing during its first year of operation, I'd like to turn the conversation over to Dr. Klaus Pontoppidan from the Space Telescope Science Institute.
All right, thanks, Eric. Yeah, you're right. We're very excited that we now have the first year of JWST science fully defined. This is actually a relatively recent event. Only a couple of months ago were most of the time defined in the sense that programs were selected that the worldwide scientific community could use. And the way that this is done is that there's a process for anybody in the world who has a good idea. Any scientist can submit a proposal, and then this is evaluated by peer review of the same communities. So we had late last year about 200 investigators or 200 scientists from around the world were looking at this submission, and were ranking them according to what science was the most exciting. And the selection was announced just a couple of months ago. And so that fully defines the first full year of JWST science. Now, the representation in this selection was 44 countries from around the world, investigators from 44 countries around the world, and 45 US states, as well as DC and the US Virgin Islands. So it's truly a global scientific endeavor. Now, this is not the first time that at Space Telescope we do this sort of thing. This has been done for more than 30 years with Hubble in a similar way. The Hubble Space Telescope also awards time in this way, and in many other ways, we are really fortunate that we have had this experience with Hubble, because we can leverage this 30+ years of experience to make the best possible environment and infrastructure for scientists to use Webb. So many things are done in Hubble way with Webb, but many things are also done in a Webb way. And I think that gets to what Eric was talking about as well, is that Webb was not only built to do what Hubble did, but better. It was also built to answer questions about the cosmos and about our origins that we cannot answer in any other way. It cannot be answered by having more Hubble time, for example. And so some of that comes from the things that we could do with Hubble. There's a little bit of overlap in capabilities between Hubble and Webb in terms of parts of the electromagnetic spectrum that we see. And in those areas, well, Webb is bigger, so it's better. Right? It's 10 times, 100 times more sensitive. But there's a large part of the electromagnetic spectrum that Hubble just doesn't cover. And in that area, there is just no comparison. The science that is done in that region cannot be done any other way. And so we were really happy to see in the programs that were selected that people out in the community, they realize this and they really are using Webb in this way. And so one way to look at it is that there are many exciting programs in the first year that addresses questions that we didn't even know we had until a few years ago. So these are questions that obviously the Webb could never have been designed for, because it was designed long before a couple of years ago. So let me just give you some examples of that. Like let's think about the cosmos, for example. Just in the last few years, there's been attention in different measurements of the rate with which the universe expands, and different types of observations find different answers, and we don't know why there is this difference. Well, there are observing programs in the first cycle that will look at answering that question with Webb. We have had these amazing images of supermassive black holes in the centers of galaxies that were obtained with the Event Horizon telescope, a large radio interferometer. Well, there are proposals that will go and look at those regions and understand the environment using the infrared capabilities of Webb to penetrate into the centers of the galaxies and understand more about those supermassive black holes, including the one in our own Milky Way center. There were the discoveries of gravitational waves, right? So these waves come from mergers or collisions between black holes or neutron stars, across the universe, that were detected with gravitational wave telescopes. It was predicted by Einstein long ago, but finally seen. Nobody anticipated that those discoveries would happen, but their programs with Webb to go and follow up on some of these collisions, particularly between neutron stars. And that's particularly interesting because it is thought that the debris between neutron star collisions give rise to the formation of elements important for us, something like gold, for example. So one of the capabilities of Webb is that you can take spectra of the debris of such events, and you can use those spectra to determine what they're made of. And in that way, you can try and answer, are they really actually forming these elements for the first time? We can go on. So, for example, in the past few years, we have gotten these images with ALMA, the Atacama Large Millimeter Array, of protoplanetary disks, so disks forming planets around other stars. They show these beautiful rings and spiral patterns that are evocative of interactions with young planets embedded in the disk. We haven't seen those planets yet. There are programs with Webb to go and take images of those very same disks to try and see if we can detect the planets that ALMA suggests are there. We can also use the spectroscopic capabilities of Webb to tell what the material in these disks are made of, and particularly look for water, complex organics, and other chemical compounds that are important for life as we know it. And moving on to exoplanets, there's a tremendous amount of programs doing exoplanets. But just to mention a few, there's some that try to understand general properties of exoplanets, and there's some that look at exotic worlds. There's a program to look at the nearest stars, Alpha Centauri, and image that and look for planets in that system. Very exciting if they find something. There's a program to look at exoplanets orbiting so close to the central star that their surfaces are molten. They have clouds of rock and they may rain lava. Webb will be able to look at those and actually tell if that is the case. Are they raining lava? And we can go all the way to our own solar system. Right, we recently had the New Horizons mission passing by the Pluto system. I thought that was so fantastic. I was so excited to see those amazing images of the Pluto current system. But that was just one example of a population we know is out there. There are many Pluto-like worlds out there that are frozen fossils of the early formation of our solar system. What Webb enables us to do is that we can actually observe all of those large numbers of them, to measure what they are made of and get a much more whole understanding of our early solar system. And then finally, we had these discoveries of extrasolar comets. So comets from other stellar systems that have been ejected and by chance have passed through our own solar system. It is thought now that that is actually a relatively common occurrence, and there are programs in the first year to make sure that if we find one of those during the first year of Webb science, Webb will be able to go and observe it and understand what it's made of and understand whether the composition of those objects are similar to comets in our own solar system. Again, not something that would have been predicted when Webb was made. And so we think this is really going to be characteristic of Webb, that it will continuously break new ground. And so this is just the first year. And in the following years, hopefully we'll have many new exciting programs that are based on previous JWST observations, and we'll continue to make strides every year. So with that, I thank you.
Thank you, Klaus. That's wonderful. Now we're going to go to Bill and Scott because we have a couple questions that came in. First question is from Paul Marks. There is currently much work going on to perfect PROXOPS, orbital proximity operations, to refuel satellites or to repair them using robotic spacecraft. When Webb is on station, it's at a very lonely spot out at L2. Is there any way that any technical problems might be fixed by such a visiting robot?
So the JWST, unlike Hubble, was not designed to be serviced. Maybe some creative engineers can come up with ways to do some type of servicing on it, but really what we've allowed for, we've put targets on JWST to allow for refueling. So if we get to the point where we're starting to run out of fuel, they might be able to mount a mission to go out and refuel JWST to keep it going.
Thank you, Bill. Another question came in from Leo Enright. Can you be specific about launch windows? The current target is October 31st. What alternate launch dates are available before year's end? Are there many or are there few? What time of day is the October 31st launch for TV planning?
There are many. We are not unlike a planetary mission. We have launch windows almost virtually every day. They'll vary in length and size. They're typically in the morning. We don't have the exact time yet for the October 31st launch date, but we have multiple opportunities for launch if we have a weather delay or whatever type of delay that may occur.
Thanks, Bill. There's a question for Scott from Don Heydrich from CBC Canada. Are there any cameras mounted on the exterior of Webb to monitor the complex unfolding sequence?
No, we've been asked this a lot, and one of the primary reasons, really just to explain why, is we have a telescope that operates at -400 degrees Fahrenheit, always in the shade, always in the dark. It's going to see light, but from its perspective. And then on the underside of the sun shield, we're almost +200 degrees Fahrenheit, always in the sun to convert sun into electricity. So that's where you would also communicate data. That's where the instruments dump their data, so to speak, to a recorder. Every wire that goes from the spacecraft to the telescope can affect the mission. It can conduct thermal energy. It can conduct a dynamic vibration. So this observatory, to be so thermally and dynamically stable, is really stripped down to the minimum of literally every wire that goes from an instrument to there. So adding cameras was considered, but it actually adds a lot more complexity than anyone would ever believe. You know, again, to have this camera at -400 wires sending data to a solid state recorder. So as we looked at it, it wasn't worth taking, say, the risk of adding things that could maybe even affect the mission. While that will be exciting data to have, and I know Bill can mention, there may be some cameras on the rocket that see it go away.
Right, there may be a camera or two inside the fairing that'll allow us to see JWST as it leaves the rocket. But right now, that's the only plan for cameras.
Yeah. So
Thank you. Another question from Marcia Dunn. What precautions and safeguards have you taken to avoid a Hubble flawed mirror situation? In other words, what did you learn from the Hubble mirror problem that you've employed to make sure Webb systems are 100% good? Thanks.
So in the development of the mirrors, there was numerous activities that occurred. One was the formation of a product integrity team that was made up of optical experts from all around the world to look at every step of the manufacturing of the mirrors all the way up through testing. But the really big risk mitigation that we did was down at the testing of the telescope down at Johnson Space Center in their Chamber A. This was the chamber that was built back in the Apollo area that was modified to become the largest cryogenic chamber in the world. We were able to deploy the entire telescope. When we went through the entire mirror alignment focusing process there, and we were able to prove on the ground that we do not have the problems that Hubble has. In addition, each of the mirrors that you see behind, the segments you see behind me, have motors on the back of them that want to allow us to align it, but also allow us to change the shape of their mirror a little bit so we can go in and make adjustments to that mirror if we have to.
Thank you. Another question from Nancy Atkinson. Dr. Vila mentioned a process of figuring out which image comes from which mirror segment. What's the name of that process, Begoña?
It's called wavefront sensing and control, and it involves a very careful, detailed set of activities. And we have Lee here that will be able to give more details afterwards. But basically, you find the stars, you can move the mirrors, see which one moved to know which mirror it belongs to, and then start using those actuators that Bill indicated, making them all together and focusing as needed.
Great, thank you. Another question from Emily Speck of CBS Orlando. During the first year of James Webb's life, how will researchers selected for observation hours learn how to use the telescope? Can you talk about that learning curve with a new telescope? Klaus, would you be able to take that?
Yeah, no, that's a very good question. We've been working for years to train the community through a wide range of different types of training events. So this is both in training how to use the telescope, so how to propose for it and how the operations work. And there's in the ground segment there's a system called proposal planning that helps users to do that, and it's a lot of work to do because you have to, it's essentially a service tool that allows people to have access to such a complicated piece of machinery in a way that doesn't take too much time. We also run training events right now, actually, that is meant to help the community understand the data that come down. We do have software that process data up to a certain level, but we expect investigators will want to look into the data in much more detail. And so we have training for them to understand the basic processing of those data, how they might be able to analyze them in greater detail, and we provide tools for that too. So it's a fairly big effort.
Thank you. I have a question from Jeff Faust. What is the status of launch vehicle readiness for Webb? Ariane 5 has not launched in 9 months, and there are reportedly payload fairing issues on past Ariane 5 launches. How many Ariane 5 launches are scheduled ahead of Webb? And if those are delayed for any reason, will Webb's launch also slip? Greg?
Yes, also a good question. I think that 9 months is about right. So we have 2 launches before Webb. So we're number 3 in the manifest. And we continually work with ESA, one of our 2 international partners, providing the rocket, the Ariane rocket. So that they're going through the process of getting the rocket ready for the upcoming launch, the first one of the 3. And so we're following that schedule. They're providing us updates on that. And once they launch, we'll be able to launch in about 4 months after that. So that right now, that's the plan.
Thank you. Another question for Greg from Leah Crane. How do you plan to ensure the spacecraft safety during shipping?
So We work with some of our other government partners to do safety and risk assessments for shipping. So they look at the passageways, any particular threats. They've done that. Right now, we think it's a pretty safe way of travel, and they would do a follow-up on that about 30 days before we actually ship. So right now, we think we're in pretty good shape, and all of the details of safety and risk, the shipping companies and, of course, the project team, Bill's team, they know how to do that.
Thank you. A question from Kenneth Kramer. Discuss any other solar system observation of targets in the first year, like Europa, Titan, Uranus, Neptune, and their moons. This could go to Klaus or Eric.
Yeah, I can take that. Yeah, so there's a fair amount. I believe it's 5 or 6% of the time is spent in the solar system. So Webb can observe any solar system object outside of the orbit of Mars. And so that in effect actually does include programs in cycle 1 to observe the Jovian system, moons, Uranus, Neptune. I mentioned the Kuiper belt object, trans-Neptunian objects, comets, asteroids, you name it. So I think we have actually very good coverage. You can expect to see some exciting results in the solar system.
Thanks. Another question came in from Jonathan Amos. Can you say something about the process of how Webb will be transported to French Guiana? How will that be done? How long will it take? And how much support equipment do you need to take? Bill, would you like to answer that?
We go to French Guiana via ship. We no longer fit inside of a C5. We barely fit when we were just transporting the telescope around. In addition, going to French Guiana, if you were to fly to French Guiana, there are 7 bridges between the airstrip and the processing facilities, which would not withstand the loads of JWST going across them. So we had not much of a choice but to go by ship. We will leave from California. We will go down around through the Panama Canal and then over to the launch site to unload. You have to account for getting through the canal. That could take a couple extra days. So, 12 to 14, 15 days it takes to get there. The shipping container is fully environmentally controlled. We will have folks from the project on the ship to monitor those environmental control systems. And we do a full checkout of that once we get down to inspections, once we get down to French Guiana and to the launch site.
Thanks, Bill. Let's open it up. Do any of the reporters in the room have any questions?
Hi, thanks so much. Chelsea Goad with space.com. I know that Webb and Hubble will be obviously operating at the same time if all goes according to plan, which it seems like it will. Is there any plan for the instruments to take co-measurements in any way? Will researchers be able to apply to use both telescopes? Will there be any sort of collaboration on orbit?
So in the first cycle, we're not combining simultaneous observations from other observatories. I think it was just considered maybe just a step too far for cycle 1, but it's definitely something that is considered in the future, other ways to synergize between Webb and other observatories, including Hubble, where it makes scientifically sense. Yes.
Hi, thanks so much. Jay Bennett with National Geographic. I was wondering if you could tell me a little bit about the first observing campaign. I guess this is for Klaus, that Webb will do, 6 months after launch when everything is deployed, and check out what that very first campaign is going to focus on.
So we don't run campaigns in that sense. So we essentially we have for the first year of science, we would call cycle 1. There are different types of programs that go into that, but they all go into a big pool, and they're scheduled according to their schedulability, just what makes the observatory most efficient. The only thing that we're trying to do early in cycle 1 is what's called the early release science program, which is it's a minor fraction of the total time available. It's about 500 hours, and that program is intended to provide the community with data, everybody in the community, not just the ones who won time, because we realize that it's a highly subscribed, highly oversubscribed observatory, and we don't want to keep anybody out. So it's important for us that the full community should be able to propose for exciting science that's based in cycle 2, that's based already on observations done in cycle 1. And so that's the reason for the early release science programs. And there are 13 programs that were selected for those 500 hours. The range, across a wide range of science and instrument modes that was really meant to demonstrate how well instruments can do the science that they're meant to do, and to help others get an understanding for that. And all the data that is taken in the early release science program is immediately available as soon as it's obtained.
Thank you. So another question here about infrared from Christopher Wondrek. Similarly, what's different between Webb's orbit and Spitzer's orbit? And why are they different if both of them are infrared? Eric, would you like to take that?
Sure, be happy to. Spitzer used what was called an Earth trailing orbit. So it launched and it stayed along the same orbit as the Earth, gradually moving farther and farther away from the Earth during its lifetime. But it basically stayed around the same orbital path as the Earth. Spitzer had a tube that protected its mirror from scattered light, so it could stay in this path and just make sure that its barrel wasn't focused looking at the sun or Earth. We're going to L2, and as such, we will follow the Earth and the Moon around as they go in their orbit around the sun, and we will always keep the sun shield facing the Earth, Moon, and Sun, because our telescope doesn't have a tube or a baffle around it. It's a naked telescope. So both of these observatories use different strategies to get away from the Earth itself, a big infrared source of radiation, but both ways are effective for making sure your mirrors get cold so you can see that very faint infrared light or heat from the cosmos.
Another question more geared towards the parts of the telescope. This is from Marcia Dunn. Are there spare parts for many, if not all, the telescope parts? So there's a backup in case of failure. In other words, could you cobble together a backup telescope if you had to in case of a launch failure?
We will not be
would you like to take that?
I'll take a cut and then pass on the bill.
Yeah, go ahead.
There is parts that we have available as we were building this up on the ground. And most of them become what we call engineering models, like for electronic units that are used in the test bed. So in case we have to do a software update when it's on orbit, or troubleshoot an anomaly and simulate it on the ground. So pretty much everything has at least one of another electronic box, some cases 2 or 3. And then actuators, there's a few extra, but not all of them. There's only 1 or 2 mirror segments,
right,
that were spared, and that was really meant for in process. So no shape or form is it to build another telescope. It was meant to be available as we were building this telescope, to have them available in small quantities for the things that are big, or maybe 1 more for things we already have 1 or 2 of.
Yeah. Scott answered it exactly why we have enough for the build, but not enough to build another whole telescope.
Thank you. Another question on, if we find, from Isam Ahmed, if we find other extrasolar objects like Oumuamua and find their natural origin, might that dispel the artificial origin theory? And Klaus, you could probably pronounce that correctly.
Yeah, Oumuamua. Yeah, so that was one of the interstellar interlopers, comets from another system that came through all of it. Yes, I mean, I'm sure that Webb observations of new future objects like that will provide data and information about them that will make it much clearer what their origin is.
Thanks, Klaus. Question for Eric. What is the projected redshift limit of Webb, and what is that in millions of years after the Big Bang?
Well, that's a great question. And in fact, that's why we built this observatory, is to answer that very question. Right now, I think the record redshift holder is something a redshift of 11, a little bit beyond 11. So if the universe behaves as we think it might, we could, and objects are as bright as we think they might be, we could reach redshifts of maybe 12, 13, maybe even 14. But we really don't know how the universe formed those early galaxies. And so it's difficult now to predict ahead of time what's that limiting redshift we'll find. That's why we're doing this in the first place. Great question.
Thanks, Eric. Yeah, let's ask some of the questions that came in from social media. So this is from Instagram. How are you planning to take care of the mirror in space? There's probably objects like meteors which could collide with the mirror and break it. What's the plan for that? Eric, would you like to take that?
I'll give a quick answer. Maybe Eric can jump in. One of the things I'd want to say is we endure the space environment, but first of all, it's been characterized by us by some other telescopes or instruments that are out there like Gaia and Herschel and Planck, so we know what the micrometeorite environment is in L2. And this is designed to withstand that, meaning it will get hit with micrometeorites, and with that, it has the toughness to go its entire mission life with, call it small blemishes. And the mirror itself and the sun shield in terms of pinholes, and we prove that out by actually taking this hardware into a micrometeorite accelerator chamber, and we just, we bombarded a mirror segment with that, and we did the same thing with sun shield layers. So we showed by simulating the, called the cumulative space environment in a very much accelerated way that they would slowly degrade, right? That the behavior of the mirrors themselves would have small blemishes, that the sun shield wouldn't as much tear or burst, that it would have small pinholes in it, and has enough robustness in its design. So basically it's designed to be tough enough to hang out there. And we prove that out with test articles on the ground.
Thanks very much. And we're going to have Eric, go ahead.
I was going to follow up. Scott's exactly right. And the way we specified the observatory's capabilities took that all into account so that even after experiencing all that, it still meets the science needs.
Another question came in from Emily Speck. What kind of implications could James Webb have for future generations of scientists or technology that may not even exist yet? Klaus, would you like to take that?
Yeah, I can take a stab at that. I mean, it's clear that Webb has pioneered a whole long list of new technologies, and once we're in orbit and we're operating, we'll have a lot of things to learn about how that technology works. And I know some of that flows already into the next generation of space telescopes. So there's an ongoing process that's been going on for a few years in the US anyway. It's called the Decadal Survey, which is the process with which the American astronomical community gets together and decides on what are the highest priorities, what does the science need in terms of future technology and future hardware and future telescopes. And they are preparing or have prepared a large report on that, and we're all waiting expectantly on that coming out, because it'll have a recommendation for what the future should bring. But I know that a lot of the concepts for future telescopes that are in that report are based on lessons learned from previous space telescope, including Hubble, and it also includes lists of new technologies that are needed in order to make those future telescopes. So that'll be very exciting.
And this question's for Dr. Begoña Vila. What are you most excited about with the telescope?
That's a good question. I think we all have it in mind. There are all the great science that is being indicated. I think we're all looking for the extra unexpected things that we don't know about yet. So I think that will be very cool. I think the whole deployment and early operations will be super exciting throughout, and then the science to come. Yeah.
Thank you. And I'm going to ask all of our speakers for their closing thoughts, starting with Greg.
It's tough going back and forth with the mask and glasses at the same time. So again, thank you for participating. I think it's very important to continue the interest and the excitement around Webb. You've heard it's going to produce amazing science, science that we've never even thought of. Some people have, that's why we're building it. But certainly for the next generation, we're going to learn some things that are going to put them way ahead of the game from where we were. So again, appreciate that. We are getting close to ship and launch. So there's a lot of excitement around that, and then that next phase of commissioning. And I will be excited as well, looking for those little images. And I do have 3 young grandsons. They like to watch launches, so we do a lot of that around the TV. And I know they're going to be pretty excited also about the science. So I look forward to telling them about that in about a year. So again, thank you.
Thanks, Greg. Let's go to Bill and Scott.
Yeah, from a project standpoint, we are extraordinarily excited about where we're going in the next few months. Getting ready for the final phases here out at Northrop Grumman, shipping, and then getting down and processing for the launch site, and going through on-orbit operations and going to normal ops and getting ready to see all that great science.
I mean, for me, this project from Northrop has been here since 2002 when we won it, and so it makes it about a 19-year-old. I got 20 and 18-year-old daughters that are in college already, so we want this one out of the house. So we get the middle child, out of here and on orbit, and then of course, the amazing science. I joke with elementary school children that if you're only 13.5 billion years old, chemistry would have been easy because there's only neutral hydrogen and helium, so only 2 elements on the periodic table, and then things got more complicated, and we get to see how that happened, right? How science books got tougher and now they're going to get rewritten. So anyway, it's incredibly cool.
Begoña?
So it has been, I think, an amazing journey with all the comments that have been said. And also, it is an international collaboration. So we have worked with the teams, not only here in the US, but our counterparts from NISA and Canada. And I think I find it an amazing journey, and to see now we're almost there and look forward to the realization of all of our work with the operations on orbit.
Wonderful. And Eric?
As we get closer to launch, there'll be lots of outreach efforts at NASA, in Europe, and in Canada. And we want to bring the world along for this next great mission. It's NASA's vehicle for the deepest space exploration, and we want you to join us. So look for us. We're coming soon.
Last thought, Klaus?
Yeah, I would say I can't wait for the day when we sit at a console and look at the first science data come in. We have been working on this I personally for 11 years, and many others, many more years. We have simulated what they would look like. We have speculated. We know where our limitations are. We can only extrapolate so far. So the day that the data come down and the rubber hits the road, it will be a fantastic day, and I can't wait. And as Eric said, the whole world will not have to wait long to share in that and see that data when they're available.
Thank you so much to all of our experts and to all of the reporters who came out, and to everyone who participated online and the audience at home. Please keep asking us questions and we'll be responding to them. You can write to myself, Laura Betts, or Omar Torres if you'd like further interviews set up. For the reporters, we're happy to accommodate you. And if you have any other questions about the telescope online, don't hesitate. #NASAWeb and Ask NASA. Thanks so much for the privilege of your time. Have a wonderful rest of your day. Take care.